prohibited from recording.
Oh,
So
okay.
you're live.
Awesome. All right, so this is our second lecture that we're dealing with. And as I said before, since this is an independent study, hopefully we'll have a bit of, and you're all upperclassmen and graduate students, we can hopefully have some good interactions as it goes on. Last time we were talking basically about the computer systems that we're in, and this time there's a bunch of little topics. This is, at the beginning, we kind of hit a few general ideas. So this one has power, and it's got, cost, and we've got reliability. So we hit a bunch of different things. If we have time, I'll start getting into some performance metric areas. So my big goal on this time here together this morning is to kind of bring out the ideas of what's going on inside them and make sure that you get the concepts. The bigger part of this is going to come into where do you fit on this. So when we deal with power, there's really two kind of big areas, for instance, that we deal with power. You can deal with power when you're designing individual computer systems that are going on or on the chips themselves, and then you're worried about the heat production in them and measuring information about how long you can use a battery, things of that sort. The second end the power comes in to get you is if you're dealing with large numbers of clusters, and now power becomes A, the cost that you're going to have to pay to buy that electricity, and B, the resulting amount of heat you're going to produce, and therefore have to air condition it to be able to make this run efficiently as it's going. So let's kind of start off with some basic things on where they come. All computers that we deal with are built on transistors, and in particular we use FETs. Because we're using FETs on everything, that means in essence the control is based off of a capacitor. So for instance, in a simplified section we can deal with an N-type. So I've got, say, silicon dioxide layer, and I've got a metal. So I've got my simplified transistor that's being set up. Now, when you're dealing with a transistor in this sense, in order to be able to get anything to flow between the two sides, you need to have the charge carriers, a bunch of electrons available right in the channel underneath. The way in which you get those, since you can't directly on a normal transistor like a BJT, you would just induce a current across, which will then raise your potential, and then you'll get current flowing across the other direction. Here you can't do that because there's no connection. Silicon dioxide is an insulator. Because it's an insulator, in order to get these charge carriers to create this little N channel down here, you've got to attract them by, in essence, getting a whole bunch of positive charge to the top. Now, by getting that situation in, the plus on the top attract the minuses, and now I've got what looks like an N-type material going through. Now this is going to result in two different things that are going to happen. If I want to switch this so that it's no longer conducting, right? So this shows a connection. It could be a plus, for instance, or a minus, whatever, right? I've got a connection that's going on. To get to the other state, I have to disconnect, which means I have to discharge the capacitor. So this is why going 0 to 1 or 1 to 0 is always going to come across as a charging or discharging capacitor. Since you're basically building everything out of a large number of FETs, you're going to have a huge, complicated interconnection of parallel and series capacitors that are going on. The likelihood of you predicting this mathematically is low, so usually what we do is measure it by taking a look at the actual system that's going on. We measure how much power is being used, and we'll calculate it backwards. But this at least is the reason why it's a capacitor. Now, once you've got that it is a capacitor, we now say, okay, capacitor, I need to look at, for instance, how much energy I'm going to have to use to flip this or to charge or discharge it completely, right? So to do one single direction, that's 1/2 CV squared. So that's how much it takes to charge or discharge a capacitor, because that's the energy stored in the capacitor. So I either have to give it that much energy to set up the channel, or I've got to remove that much. either way, that's what it costs us to do. Now, I don't just do one of these. Your whole system is doing a huge number. Now, we can't really talk of an instantaneous value, again, because it would be A, too hard to calculate, and B, it wouldn't be particularly relevant to us. What we really care about is kind of a typical amount of energy we're going to be using in a period of time. Right? Now, energy used in a period of time is power. So therefore, the power that we're going to deal with is going to be an average power. And that's going to be 1/2 CV squared divided, or over our time period. So in this case, what we're going to get when you're dividing by time is multiplying by frequency. Right? So that is the same as dividing by our average time, because that's the time period we care about. So this gives us an idea of dynamic power and dynamic energy. I'll put the D to specify that's on here. The reason why it's dynamic is this is doing the switching from a 0 to a 1 or a 1 to a 0, so you're changing the systems in there. Originally, this is all anybody ever cared about. So once you come to a system and you start lowering the voltage on here, you know, the channel gets smaller and smaller, so you get more actual losses that are required, because as this gets thinner, you're getting, takes more and more, you get a higher resistance going across, so you're going to be expending more and more power for that signal to go through. But if you're just maintaining a signal, you're still having to, you know, pay for that resistance. So as voltage goes down, this resistance is going to increase, which means you're going to spend more power statically as you're maintaining it. There's a second set, which is the charge that you put here is going to leak. Right? So that's your leakage current that's going across, because you don't have a perfect insulator. Silicon dioxide is a very good insulator, but it's not a perfect insulator. So there's a number, my point to this one is there's a number of different power losses that are going on that have to do with current flowing. Even in the static state, you do have current flowing. Here, to read, you're either 0 or 1, you've got a leakage across there, and you have to keep maintaining the charge on here to keep that open. There's some other effects that go on. As this is flowing through here, you're going to actually get a distribution of charges that's going on. So, you know, you'll tend to get the minuses flowing down, so they'll build up on one side, so you tend to get this kind of wedge that's on. And as that happens, you get to what's called a pinch off. Right? Because on one side, you've used all the charge carriers up, and they're only being reproduced at a slow rate. It might be so slow that it actually pinches off that connection, which can cause you to get a problem across there. Now, the reason why we're interested in all of these areas on has to do with then the static power that we're dealing with. And this is just current times the voltage. Now, this is kind of your standard 101 area. Goes in. Voltage, all the same in both of these as it's going on, actually in all three of them. All right. Capacitance, we can fairly directly measure, because we can do a certain number of operations or measure a certain period over time, and I can calculate C, because I can externally measure what this was for the whole system. Just by putting some type of a load measure on it. Right? So that's not hard to do. And I know what the voltage was, so I can calculate for C. So I can find C. The challenge is the I that's in here that's going on. Now, I can do a very similar thing. I can put it in a particular state at a particular voltage, and then hold it and see what it's going to take me to do. But what you'll get is an aggregate of every one of these current measures that goes in. And so it's not going to give you just one of them. And depending on, as you keep lowering your voltage, for instance, this one's going to dominate very heavily. And that's what happens over time. But the leakage on here is also going to be pretty hefty on you constantly. So there's various factors in there that will affect those. The calculation of I is a really debated quantity. There's a fairly good paper out by Professor Rice from about 2009 or so. where they go through and they take a look at both of these two major forms and calculate them, you get a really horrible, ugly equation. It's not exactly our main thrust in here, so I'm not going to worry about it. If you get into VLSI layout, this becomes an issue as it goes on. But it will have to do with, for the current flowing down here, depends on the actual area that you have of this, and it's going to depend on how thick this goes on. Now, the reason why these parameters just to mention to you become important, we are shrinking size, so that's going to make this one smaller and smaller, but as we shrink size, we're also shrinking this gap here, which means it's going to be easier and easier for current to flow through there because you're getting a thinner and thinner layer. Now that means we have to get materials with better and better insulating properties. This is why material development is pretty crucial for the advancement of our chips as they go on. At a certain point, it gets thin enough that electrons can tunnel. Right? So this is when quantum effects are no longer ignorable. So it turns out that electrons, we often think of them kind of as a ball orbiting around and things like that. That's completely wrong. Right? We know it's completely wrong. It's a useful idea for people to kind of think of, to wrap your teeth in. But allow me to give you a simple explanation so you can understand why this must be totally wrong. How many times have you heard of an electron spiraling into the actual nucleus of an atom? Okay. So in order for something to stay in orbit, you basically have to maintain your energy around there. An electron is a charged particle. Charged particle that's moving in a field, right? It gets deflected, it's going to give off some radiation. As it gives off radiation, that radiation that's going on, those are photon packets. So those photon packets have a particular energy. So if it were following a curved path, it would constantly be emitting photons every time it curved and bent, which means it would be constantly giving off these little light packets, but it would be constantly losing energy. As it lost energy, it couldn't stay at the same energy level, and it would eventually spiral into the core. And as it got closer and closer, it would be bending faster and faster, which means it would be losing energy faster and faster. But that doesn't happen. So therefore, it's not losing energy, so it's not moving in a curved path. So therefore, you now run into one of those basic things that kind of underlie why did quantum come into being for us as it goes on. Your electrons are moving in a whole bunch of little kind of instantaneous short segments, but they're never really there either. That's even kind of a fiction that I'm giving you. It really just has a probability distribution of where it's located. Okay? And when you observe it, then it'll collapse and you can kind of see it. But in the in-between times, it's really just kind of spread. And this is why you get those clouds when we talk about the shells and everything else that goes on. It's really describing to you the distribution function that that particular electron has. So even terms like spin up and spin down are kind of arbitrary terms to help us to think about them, right, as it's going in. But it's really, there's kind of a beast of a different kind going underneath there. Since it's a distribution cloud, if it gets small enough that your other conductor is now within a reasonable probability of that distribution, guess what happens? The electron can just appear there. Okay? So this is called tunneling. So as your material that's insulating gets thin enough, the probability distribution for an electron could become big enough that the metal's inside at a reasonable distribution, in which case it can just appear there. Okay? It's still a small fraction, but with a large number of these over a large period of time, it becomes a perceptible current. This has been verified. Okay, so this is not a questionable thing. You just got to understand that is what it is. As we get smaller, you must deal with this. So the point of that one is, as we get smaller, a whole new mechanism now starts coming into play. You get small enough, now all of a sudden you have tunneling electrons that carry across, which is going to even blow that equation out. In order to do this, then, you really have to do an extremely complicated model that requires both statistical mechanics and the VLSI layout. neither of which are a main chore, but the book is correct. If you look at the introduction, they make a big emphasis that people don't mention these problems or issues to you. So people designing chips go merely along as if that's not there. So what I in the book want you to do as you're going into this is understand what the issues are, what you're going to have to potentially be dealing with, and some ideas of where to look as it's going. This will hopefully tie in if you take other courses down the line, you know, for instance, a VLSI layout, or an advanced electronics course, which will get into some of the stat mechs of how transistors work, particularly once you get the quantum effects on it. So these become kind of big issues to us as it goes on. If you're interested here at Baylor, we actually have two new people whose this is kind of their specialty area, has to deal with the quantum and the physics underneath it. So, you know, Dr. Blair, he talks about how you can make quantum level effects look classical. So how do you preserve this as long as possible before going, even when dealing with like single atom systems, which are going to run into big problems as it goes on. And then Dr. Olofsson is, because of her physics background, she's looking at a lot of stuff on lasers and things of that sort, but is looking at the quantum effects and has done layouts. So these are areas that'd be, you know, if you see courses from them, you might want to take a look at if this is interesting to you. So for us, this becomes just something we're going to measure. And the way in which you can kind of measure this, since I can calculate this, and your total power is just the sum of these two. I know really well what this is going to be. So therefore I can easily calculate this one out, and then I can take a whole bunch of different measurements at different voltages, which will allow me to then fit a current to this. You just got a bunch of data points and then you just fit it. And that, for our terms, is more than good enough for what we're going to deal with. The book even simplifies it beyond that, often just saying assume that the current's about the same for a small operating range. Yeah. Things of this sort as they deal with on some of the problems and areas of that. That's simple enough. In a real system though, I would actually take a bunch of measurements and fit to it if it were me. So just gives you some ideas as it relates to these areas and going on. This is the basic underlying idea of where power is coming from and how you can deal with it both in real life and then the book, just taking this as a concept. Does that make sense to everybody? Okay, some takeaways. We get into design aspects that's going on based on these. So let's say that I'm now dealing with an embedded system, or I'm dealing with a small cell phone or something like that, right? Where I've got a very limited supply of how much energy I have stored in a battery. I'm running on this, I want to make it last as long as possible. These equations govern what you can do and how successful it's going to be. So let me ask you, if I'm just concerned with how much work you're actually able to get done, right? Work being described, you're trying to do some calculation, it's going to take a certain number of operations to finish that, which entails bit flips and data manipulations. Which equation up here is going to really heavily govern which one is dealing with how much work you can accomplish? Right? How many are going to go for PD? I promise I won't hold you on it. There's a few people who didn't. How many go for ED? Got one brave soul, okay? So let's remember, in order to get through each of these, we've kind of ruled out static in this case as it's going on, because what I'm mainly concerned with is getting the job done. If I do it really fast, that's going to become very small. If I drag it over time, it's going to be longer. So this one directly doesn't govern that, but my solution technique will be affected by it. But which one's really governing it is going to obviously have to be up in the dynamic. That's what's describing what's going on. What's power? And so we've got these three quantities, right? Energy, power, and work. How do they relate? So this is kind of evil because you're all grad students and I'm asking you about freshman physics. Right? But there's a reason we make you take freshman physics.
Isn't it energy and work are dimensionally the same?
Yeah.
Energy is described as the ability to do work.
Right.
Okay? What's power to this whole thing?
Power
That
over
is,
time. Yeah.
Okay, so it's the rate at which you're using energy. Or you can think of it as then the rate at which you're accomplishing work. That make sense? So energy, the amount of energy you spend does work. Power tells you how fast you're doing it. So if I'm concerned with how much work you can do, what's the appropriate measure?
If time doesn't matter.
If you've got a job, you know, I've got to take 100 bricks from this side of the room to that side of the room,
Yeah.
right? Does it matter how much time I take to do it as opposed to the amount of work that was done?
Not for the,
Okay, so do we want to re-vote on this?
yeah.
Right? So, since I'm concerned with getting the job done, accomplishing a certain amount of work, my appropriate equation is, I'm going to go for PD. I'm going to go for ED. Across the board, everybody's right now, right? Now, the reason why I say that these are those terms that kill everybody. Right? And there's a very frequently done thing inside computers which is to deceive people that they are saving and that it's working better. So you got to think of what you're trying to accomplish that goes on. One of the most common things that happens is people will slow down your clock when you are on battery. And that allows the battery to last longer. Right? Now, that's absolutely true. Your battery will last longer. Total amount of time until the battery discharges will be more because you're doing less work per unit time. But does that mean you can accomplish more work? Clock rate doesn't appear in the equation. Right? So it doesn't actually affect what you can get done. But the battery lasts longer. So most people go, yay. Okay, now, there's kind of a second thing that I put in here. This argument up to now assumes something. It assumes that you are using your device at its full capabilities. If I slow down your clock, and you're really just not doing very much anyway, right? You're not taxing the system, things like that, then it will turn out that your battery will last longer because you would before have been wasting a lot of power on unused things. So, you know, if what I get down to is concerned of power, then I can relate this down to just how much is going at a time, and I can reduce the rate at which it's going out. And maybe there was a lot of wasted stuff that was going on and I can dump them. Because let's be honest, our computers and our phones and that have a lot of background things running. Not all of them are necessary at every instant. So when you go into a low power mode, if you do something wise, like turning off some of the higher requirement systems that are out there, so your computer is not doing as much, it'll now last longer. What you're doing is probably fairly low if all you're doing is sending something texts and things like that. So you're probably not stressing that system. So the longer power thing, since you weren't using all that power, was being used for a bunch of other stuff, you're probably going to get a net benefit. So this is where that kind of trade-off. You have to look at what the situation is to pick the right equation. If that person is hard driving it, you have to go here because they're accomplishing work. If some of that work can be removed so that we're only concerned with how long does it last, because they're doing so little, it's well below, you know, the nominal operating amounts that go on, kind of like somebody sending a text or things of that sort, this becomes the dominator. And this introduces another parameter to us which we like. Now, I can, of course, for both of them, I can drop the voltage. If I drop the voltage, how effective is that going to be? If I cut your voltage by 10%, how much do I save?
19.
19%. Right? This is a pretty sizable way to get things because it's square. That's going to get you an awful lot when it's going through. So this is a really wonderful parameter. Caveat. You lower the voltage, what happens? Lower the voltage, I thin the channel, higher resistance. So what happens here? It goes up. Okay? There is a trade-off. At a certain point, you lower it so much that you have not made a channel anymore. That's the minimum voltage to turn that on. Depending on your system, it can be anywhere from 0.7 and up. There are systems out there now that can get slightly below a volt for their operating. There are a decent number there at 1.1, 1.8 is a pretty standard voltage going out there for chips. Right? But the lower it goes, this is why. And the reason is that if you watch the curves of what were going on, computer performance was being driven by increasing your clock frequency. So as the years go on, so this is time, right? If you looked at your clock frequency, you just watched, and the clock frequency was going up, 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 up in a nice, pretty straight line period for about 30, 40 years that was going on. And this is what was driving computer performance continuously that was going on, right up until 2003. Anybody tell me what happened in 2003? We've got a limit. You're using all this area. We talked about energies related to work. Right? Power is what? What's it related to? The heat you're pumping into it. Okay? So that tells you the rate at which heat is being built up. Well, at a certain point, you've got an issue. Your chip is doing processing inside a volume. So that volume, if I consider this just simply for a square thing, the volume is related to S cubed. What's your heat dissipation based off of? It's got to go out the side, so it's proportional to S squared. So as you're building up your clock frequency, it's also increasing the heat production. So at a certain point, you reach the area where this, and there's not much you can do about this one. You want more functionality, you've got to put more transistors in there. So you are basically putting yourself up against a wall. In 2003, we hit the rate at which you hit the limit of air cooling. Any performance increases out there cannot be gotten by increasing the amount of power pumping into it. Because you just can't cool it fast enough and you will burn your system. So if you've watched, we hit 3.2, 3.4 gigahertz in 2003, which is still reasonable numbers right now. So they were talking the next generation system was supposed to be 5 gigahertz that was going on. And they actually built them, didn't last very long. That's where we get into the whole idea of reliability. It turns out heat and reliability are inversely related. So the more heat, the worse it gets. And they discovered those systems just could not be made reliable that goes on. You can handle it for a short period of time. If you've got low activity, you can kind of do a burst of activity that's beyond your heating limit, and you can use the heat capacity of that system to kind of absorb it and then spread it out and then eventually go on. That's basically where we go on. Yeah.
Now you said air cooling, so what about liquid cooling?
Yeah, so you can go to liquid cooling and you can get a better density of where it goes, and you could theoretically clock it higher. So if you watch on some of the systems, they will actually do liquid cools as it goes. The problem is liquid cooled systems are not super reliable. I mean, I've actually built several, I've run them over the years and things like that, but trying to keep them up is really difficult. Their downtime is horrible because you got all these liquid tubes that go in, and you got to get the right liquid so it won't cause any corrosion problems. Corrosion causes a thermal boundary layer inside there and it lowers your heating rate that goes. Very few manufacturers, because of reliability issues, will ship them that way. So you've now got to remove something and reattach, and if you don't get a good job reattaching them, you're in some deep trouble. And the common problem that goes on when you're attaching them, there's kind of two ways. You got the paste and you got these little thermally connected squares. If you do the paste, you can get air bubbles. And we often think of air as really cooling to us, but it's not. It's a great insulator. So air is actually what really gives you a wonderful, wonderful thing. Your fluffy, loose blankets and that have lots of air pockets. You just want still air that's going on. So you get that in there, you'll get a heat buildup underneath and it'll never make it to the heat sink. The squares have some of the little, conductive, thermally conductive squares they put down, have their own issues. I've had those things pop off and all kinds of stuff that goes on, depending on the reliability of what they get impregnated into the material, and it will depend on how well they work. So, you get some issues on that as it goes, and then you get all these leaks that happen on. So there's just, it's an issue where it goes on. Now, Cray was very early in this and identified this early on. You'll see some of their systems actually, they had ones where the boards were, actually in liquid cooling systems and all kinds of stuff. Then you have to get, liquids that aren't gonna actually conduct on them, and, then they went to a variety of other ways of pumping the liquid around. So it's got its issues, but yeah, absolutely, you can do that. But now you have to worry about this is a mechanical engineering problem of most liquids flowing tend to be very bad to the materials at which conduct nicely. Because a lot of those liquids want to react with them. And you can find liquids that do it at a lower rate, but you're not gonna find some that don't do it at all. So.
Is there a reason we didn't increase the chip size without increasing the functionality? Or, increasing in such a way that we have more service area?
So so that gets to the next thing, which has to do with the cost and the yield of what goes on. When you're doing a chip and you're building it, I think this one's easy enough to understand, I can erase it. So you got a wafer that's going on, you get a particular die that has all your patterns that are built up, a series of them, and they're gonna fill this wafer as it's going. Right? So imagine I completely filled this whole thing with each one, where every one of these is an equal identical die that's in there. You're gonna build them up as a series of layers. You do this inside a clean room to make sure that you don't get junk coming in, because you apply material on and then you do the mass and remove stuff. Well, what happens if a little particle dust comes in? Right? Or what happens when copying this, you get an error on a particular chip, just life happens. Right? Now, those things are going to occur. Defects occur. This is the main mechanism which defects go. Once you take these and you separate them up into their individual dies, you have to test them individually to find out, did this one work? And then you have to bond it to a package, and then you have to test if it works. And you do these whole series of build up, every time checking, because sometimes you can find them and you can see what the problem was, and sometimes you can fix it, sometimes you can't. Right? So this determines what your yield is or the cost. Well, if I increase the area of this, since there's a certain rate at which defects go that's based on the area, a bigger area becomes more defects. So if I quadruple the size of this, you're probably going to at least quadruple the likelihood that you get a defect on it, and it could very well be a game-ending defect, and then you've thrown away a big chunk of your silicon. Whereas if I've got a small one, that means I'm going to only lose a little area of my silicon. Right? So the overall cost that goes on it. So if you don't do that, it becomes cost prohibitive. That's really where it comes down to. That's one of the big drivers. We want to make it small so it fits in your pocket well, but we want to make it small so it's more manufacturable. Less likely to get defects, which means it lowers the cost, means we can sell it better. So, those are great questions, and you want to think about them, because this is why I'm saying, if you think about in terms of your fundamental physics and fundamental processes, you can start seeing what's the trade-offs and how can I make these trade-offs better that's going on. So that's really kind of where our issue goes on here. The book will talk to you about how many chips you can fit in here and things of that sort that's going on. it's actually a really simple idea. I mean, you could obviously count them, but before you've actually done the layout, you can make a good guess by guessing about how big, a number of transistors will tell you about how big the area is going to be. We've got some general guiding rules of them. So you go to different companies and you'll get, they have their own little heuristics of where those come in. So you can figure out about how much the area is going to be in advance to predict it. And then if you just take the area of this whole wafer and you take the area of the individual ones that's inside here, what's predicted by how many transistor count is, you'll get a pretty good idea, but then you'll have some wasted ones on the corner, right, that are partials. So you want to remove all the ones on the outside edge. So you take the circumference of the whole chip and you divide it by the diagonal. And that'll give you about how many chips cross the boundary zone. So the book develops this really fancy equation with pi and all kinds of stuff going in there, and that's all they're doing. So go back and look at it, and that's, I mean, they don't really give you a big explanation of what it is, but that's what it is. And it's just designed to ballpark the central area, remove the outer skin. And then if you combine that with, they then give you a very fancy equation that was just done by data fitting. Remember I was telling you that you can get all these defects per area that go on? Well, over a large number of years, we've collected a lot of data. Right, so based on what process you're using, we found, you know, that you can fit this kind of by this little exponential type distribution. Right? It has to do the exponent, you know, has to do with, you know, the areas, and then the processes will affect the base and things of this sort. So it's a complicated looking equation, but that's really what it's going on, is how likely is something to hit. So, you know, that gives you what your yield's going to be. You know, did it get hit or damaged? So that's kind of where that goes. You obviously want the higher yield. The higher yield means the money you spend to build it is going to things you can sell, so then the cost per individual thing is lower. And you just take the total cost to produce everything, even the broken ones, and you got to recoup that in what you sell, you know, with some profit on it. One of those basic things is by the time you hit the end of your manufacturing cost, right, you just now start doing the doublings. You know, whatever it took you to manufacture, what you have to sell to your next upline, you have to sell to them, but at basically almost twice the cost. Because there was other things besides the manufacturing that went into it, those costs, they got covered. So you figure about 100% overhead. And they're probably going to double it also, right? As they go on to the people who are going to do the integration, and then they're going to double because they also have 100% overhead. So it ends up being about 8 times the cost of what it is by the time it comes down to the consumer to pay for everybody else who has to do all these other integrations and sales and marketing and everything else, and that's what all that comes out of. If you don't consider that and you don't consider the power and the heat load, you're not going to be able to sell the system. It'll burn up, or nobody can afford it, or whatever else. So each of these carries in. The other thing I'm going to mention, you know, everybody always says you can't really change C. That's actually not true. I can't change the material properties of C, but this is made up of a whole bunch of little circuits. So I can actually affect this by turning off circuits. Right? So, you know, now often we don't do that by recalculating C. What we usually do is calculate these for subunits. And then when you come into them, what we can do is we can just turn off the clock. So we'll make a separate clock that's synced, usually by a phase lock loop, to a main system clock. And then all I have to do is turn off the clock to that subcomponent, and that subcomponent never is able to switch. The registers hold it constant. So all your dynamics go away. But what doesn't go away? Statics. You still pay for it. So the latest trend that's going on actually dynamically powers down the sections. Right? That way both of these go away. But now I got a reboot time. So you better make sure you meant that. Right? So there's everything there is. If it's for a very short period of time, it's a big waste. If it's for a longer one, it's awesome. Like reloading cache, it's going to get a huge, huge energy cost to reload that cache. So if you turn off completely your cache, you will save power. Only if it's for a long period of time. Because you could get killed also by the reload times. So you have to very well predict what's the load looking like. Do we feel good with these areas that's going on? Right. Those are trade-offs you want to think of, and every time we're building systems, you should be thinking about this. What's this going to cost? How can I use it? Am I saving dynamic or static powers? Okay, we have a little bit of time left. I'd like to at least introduce the ideas behind reliability. This comes in very heavy at the end of the book at 6. My experience is if you see it a little bit before, then it'll help you actually remember it later when it comes. So I want to talk a little bit about mean time to failures, mean time between failures, stuff of this sort as it's going on. The book does this in kind of a very heuristic way, mainly because they're going to come back to it later. But this is the one time that you really kind of get exposure to the math behind it. Now, pretty much everybody, if you ever read one of these books, particularly once you get out to industry, they tell you, assume your product's failure rate is exponentially distributed. Right? And then they tell you this makes everything easier. It does make everything easier. Right? But the question is it a good assumption and why? So let me give you the kind of the quick rundown of why it is. And this relates to how, if you take a look at your measurement areas, this is failures, and this is time. You're going to get a really odd-looking curve for most products. This is called the bathtub. Okay? So this is what usually happens to almost every product, and it really doesn't actually matter very much whether it's electrical, mechanical, whatever, as it goes on. They pretty much all have this type of a curve. Some variant of it, the slope can vary, things of that sort. We break it into 3 regions. Right? This is called the infant mortality portion. And the reason is when you first build something, some of the things are just catastrophically failed. Like, remember those defects, and maybe you measured it in a testing environment, but it was partially damaged. So that a wire was really thin, for instance, but it wasn't broken. So somebody does a couple quick tests, boom, it worked. Right? No heat really built up because they did such a small test. But after a little bit of use, currents flowing in that narrowed area, the current will be much denser, which means the heat will be much higher. Right? You'll also have a higher resistance in it, so now your power's really kicking up because you've got higher current and higher resistance. So that area gets a lot of heat, heat causes failures, so boom, it goes. So in very early systems, you get a very high, what we call infant mortality zone that's going on. It's things that were kind of near to broken but not fully broken, just break. This is usually handled by good manufacturers by doing a burn-in time. So this period, we usually figure what is that supposed to be, and you just run it for that period of time. Now, they still will, if it fails, they can't sell it. So they're going to pass that on to you, but now it gets spread across everybody, and you're not the person who gets it done. So good manufacturers will do a burn-in time, which means I'm over here. This is at the end of life. Any of you start noticing that when you had something, I don't care if it's a car or a computer, when things start breaking, a lot of stuff starts breaking. Right? This is when the system's just kind of old, it's worn out, and things of that sort. So this is called the end of life. And if you start noticing things are breaking all the time, you figure you should get rid of this. A really good operating company or group is going to pretty much figure out when this is going to occur for their products and just replace them before that hits, so they don't have to deal with that. What's going on? Which means I'm now in this zone, which is really darn flat. Okay? When you have a constant rate of failure, that's described by an exponential system. It means at any given time you have no more information whether something's going to fail or not fail because it's failing at an equal rate. At the next incident, it's got every bit as much likelihood of failing now because it's independent of what happened before it. So that's a pretty nice area to be on when it goes in this sense to us. Right? Because what ends up happening for us is, we're in this kind of very flat zone, exponential, so that means if you look at the rate at which the failures happen, you want to look at multiple failures happening, you can just actually add up the rate. So if I have like 4 or 5 components that are not redundant, not independent, that's going, or just separate ones, any one of them fails, they take the system down. I can just add up their failure rate. Right? So it makes it very easy to do it. There's a measure called the mean time to failure. So if you figure you've got a system and it's running, fail. Fixed, running, fail. Fixed, running, fail. Fixed. You get this kind of a pace that goes on. If you average this, so you get a behavior, right, you'll get kind of this never really true, but kind of, average behavior curve, which won't tell you exactly when something's going to happen, but it'll tell you the mean time from when it's ready to go to when the average fail happens. That's the mean time to fail. Then there's a mean time to repair, such that the overall then is the mean time between failures. Those are the numbers everybody uses. Now, in real life, mean time to repair depends on your organization. Right? Now, pretty much what really matters to you is once I plug this thing in, when's it going to break? So you almost always care about mean time to fail. Therefore, what number do I report to you as a manufacturer? That one.
Big one.
The one that makes me look best. Okay? So this is kind of one of those issues that go in. They're reporting to you something that's not technically really what you're dealing with in life. That's going on. But if you've got mean time to failure, 1 over that is the failures in time. This is the rate. Right? Because this is a time period, 1 over a time period is a rate. So this is the rate. So we take the mean times to fails, we convert it to a failure in time. And now, if they're, if one thing breaks and that's going to take my system down, but the breaks are independent of each other and we're in this nice area and all this kinds of good stuff, I can just add up the failures in time. And that'll give me the aggregate systems failure in time. And now that I've got the aggregate systems failure in time, I do 1 over that, and that gives me the mean time to fail for the system. So this allows you, if you buy a disk drive that has 500,000 hours and a power supply that's 200,000 hours and da-da-da-da-da, I can take all those ones, any one of those systems breaks, my computer's down. So all I have to do is take 1 over those failures, add them all up, right? And then take 1 over that, and that gives me the time for the whole system. When do I think it will happen? It will be smaller. Right? Because the more things that you've got that could break individually and take you down, right? The likelihood is they're happening in a distribution, so one out of a large number is probably going to fail early. How many of you think you could run across McLean Stadium without falling? Across the grass?
I know.
Okay, have you noticed that once you get the Baylor line running across there, there's always a few who fall? Why? I mean, they're healthy, young people. You get a large number of things, the rate of failure starts to appear, right? You by yourself, I mean, there's also the cross interference between them, but you can actually see this effect. You get a large number of systems, likely one goes. If one of them dropped and it was all of a sudden a big embarrassment to us, right? You've got a huge likelihood that's going to be a problem in here. The way you answer it is redundancy. A large number of systems where it doesn't matter. Now that buys yourself. All right. We feel good with this? Okay. So next time we'll talk about performance metrics as it's going in, how to calculate time on a computer, things of this sort, and all that shit. Thank you very much.